So what is refraction? So refraction is the phenomena where light bends, where light is bending when it goes from one medium to another. So these are very important because in refraction, light actually goes from one medium to another. If you remember reflection, in reflection what happened? In reflection, light was bounced off back to the same medium, right? In reflection, light did not travel from one medium to another. But in refraction, light goes from one medium to another, and when it goes, it bends or it deviates from its original path, and that is called refraction. So why does it happen? It happens because the speed of light is different in different mediums. Okay, so we will talk about it in few seconds, but before that, there's something that we have to know. There's a quantity called index of refraction. So it is a quantity which compares the speed of light in different mediums. So for example, if you need the index of refraction of water, let's say you need the index of refraction of water, what you would do is you would divide the speed of light, this is speed of light in a vacuum, by the speed of light in the medium you are interested in. So here we are interested in water, so speed of light in water. So if you were interested in the index of refraction of glass, you would divide C by speed of light in glass. And this C constant is the speed of light in a vacuum, and it is given by 3 10 to the power 8 meters per second. So you will need that for one of the problems in the next slide. Okay. So usually this n is greater than 1, greater than or equal to 1. So if your medium is a vacuum, or if it is air, it will be 1. So for air, this is slightly higher than 1, but in problems you will see they always consider it as 1. Okay. For any other medium, water, glass, oil, so any other denser medium, your n is greater than 1. So this n kind of tells you how dense your medium is. So denser the medium, higher the refractive index. So you can compare n values and tell which medium is the denser medium and which medium is the rarer medium. Okay. So let's see how this bending or refraction happens. So like I said before, when light moves from one medium to another, the path changes. In other words, the direction deviates or light bends. So initially it was supposed to go, this red color A was supposed to go in this direction, right? The dotted line. But when it goes from a denser medium to a rarer medium, what happens is it kind of gets more freedom, or there's more velocity or speed for the light. So it kind of deviates or bends away from the normal. So this is your surface normal. This is very important. A normal drawn to the point. of interaction. So you can see here your light has bended away from the normal. So denser to rarer. So more freedom, right? It looks like more freedom. That's how I remember it. So if it's the other way, light goes from a rarer medium, something like air, to glass. So when that happens, the initial path was something like this. So in glass, there is less freedom. So your light ray bends towards the normal. So this is your new light ray. So in general, now you know how these bend towards the normal, or whether it bends towards or away from the normal. And there is an equation connecting all of these things. It is called Snell's law. It is a very easy one. So what it says is, when light travels from one medium to another, these angles and the refractive indexes are related by this equation. So here light travels from this medium to this, right? So if I write the Snell's law, so I start with the index of diffraction of this medium times the angle of refraction or incident angle in this medium. In the second medium, it will be n2 times sine theta 2. So it is very easy. So are you okay with this? So this simple stuff. Okay, now let's go to our first two problems. So I want you to do this and tell me the answers. So I got a lot of answers for the first one, and I'll wait till I get answers for the second one also. Okay, so do the second one also and tell me the answers. Okay. I got a lot of answers, so I will start the first one. If a material has an index of refraction 1.5, what is the speed of light through it? So we just have to use this equation. So we need the index of refraction of some material. So they have given that. So this is the equation. So we need the value of Vm, velocity or the speed of that material. C divided by Nm. C is what? 3, 10 to the power 8. Nm is 1.5. So 3 divided by 1.5 is 2 meters per second. It's a speed. Okay. The next one, light passes from air to water. So let's draw it. So this is air, this is water. And the incoming ray is at angle of 17 degrees from to the normal. So this is the surface normal. They are saying the incoming ray makes 17 degrees, 17. The index of refraction is 1.33. So what are they talking about? They haven't said the medium, right? They are just saying index of refraction is 1.33. So how would we know? So it goes from air to water, right? So in most of the problems you will see, they even don't tell the index of refraction of air. So we have to know it. N of air is 1. So in the previous slide, I kind of mentioned that, right? So we have to know that the index of refraction of air is 1. So if we know this, we know what they are talking about, right? The index of refraction is 1.33. So they were really talking about N of water. Okay. So this thing is something that you have to know. Something like the gravitational acceleration, you know that it's 9.8, right? So something like that. Okay, so we know everything. We just have to find the angle in water. And also we know, since this is a denser medium, this angle should be smaller than this 17. Even if you thought that way, there's only one answer for that, right? I said initially, so when it goes from a rarer medium to a denser medium, it comes closer than the initial path, right? That means this theta angle should be less than 17. So even from that, we can get the answer. But let's do the problem. Okay. So Snell's law. So this is my first medium and this is my second medium. So I'm going to write the equations. N of air times sine 17. So that is for my first medium, air. And for my next medium, it is N of water times sine theta. So this theta is what we are going to find. N of air is 1 times sine 17. N of water is 1.33. So I'm going to divide it by 1.33. So I get sine theta. So my theta is sine inverse sine 17 divided by 1.33. And make sure your calculator is in the degree mode. Okay, so it should be in the degree mode because all these angles are given in degrees. So when you plug this in your calculator, you get 12.69 degrees. So the closest thing is this answer. So since all these answers have an angle greater than 17, even if you knew that when it goes from a lighter medium to a denser medium, it gets closer, you kind of should know the angle you get should be less than 17. Okay. So are you all okay with these two? Yes. So this is the next one. I want you to do this very slowly and tell me the answers. There are two mediums now. Refraction happens twice, one after the other. So whenever you get problems like this, the first step is draw a diagram. So in your in the problem you have in the worksheet, there is no diagram, right? So the first step is draw a diagram. So I have a diagram here and mark whatever they have given. So first medium is air, the next medium is oil, and the third medium is water. So looking at the refractive indexes, we can see that mediums get denser and denser, right? This is a denser medium than air. In air is 1, we know that. And this is denser than that. This is even denser than that. So these angles keep getting smaller. So this theta 1 is smaller than 45. And this theta 2 should be less than theta 1 because it keeps on bending towards the normal. Okay, so we have drawn a diagram, and the next step is marking the angles. So they have given the incident angle. So when they give an angle like this, we should know what they are talking about, because incident angle is measured with the normal, right? So you should know they are talking about this angle, not this. Okay, incident angle is the angle between the ray and the normal. So they have given us 45, and we can use Snell's law to find this theta 1. And can you see that this is angles in a Z? So these are two angles in a Z, right? This one and this one. So if you remember the very first discussion, we learned about this. These are alternate angles. Alternate angles are equal. So learn about this. I think we learned about 3 types of angles. So go through that again, because in light, or where you have light, where you have to draw triangles, this becomes very useful. These two are the same. So theta 1 is equal to this theta 1. And again, we can use Snell's law to find theta 2. Okay, so we know what to do. Let's write the Snell's law twice. So we can write Snell's law to this interface and also to this interface, right? So let's look at the first interface first. So it's from air to oil. If I write Snell's law, it is N air 1 times sine 45 is equal to N oil 1.15 times sine theta 1. Okay, that is my first equation. So if you like, you can solve this and get the value of theta 1. So if you do that, you will get 37.94. So you can find theta 1 and substitute it here. I'm not going to do that. Okay. So I just wrote the value. If you got this, it is correct. So I'm going to look at the second interface now. It is from oil to water, right? So what is happening there? So it is 1.15. It is N oil times sine theta 1. That is the first part. And the second part is N water, which is 1.33 times sine theta 2. So if you have the value of this 37.94, you can substitute it here and get the answer. Or can you see this part right here is the same part as this 1.15 times sine theta? Same thing, right? So what I'm going to do is I'm going to substitute sine 45 instead of this. So one step to make the simplifications easier. So this is sine 45. Or if you don't like this, you can plug this value, okay? So we need to find theta 2. Theta 2 is sine inverse sine 45 divided by 1.33. If you do this, you get The answer 32.11. So the answer is B. Okay. So even if you if you did this, you should get the answer. 1.15 sine, instead of theta 1, you plug 37. So even if you do this, you should get the answer. Okay. If you plug the value for theta 1 from here. So are you okay with this? So always draw the diagram and then go step by step. Okay. So I'll move to the next part. So next important part in under refraction is something called total internal reflection. Look at the word. It is reflection. And before going to that, let's look at what's happening and when this happens. Okay. So let's consider a situation where light goes from a denser medium to a rarer medium. So this is the example, water to air. So anything, any denser medium to a rarer medium. So you all know what happens, right? So when it goes from a denser to a rarer medium, it deviates this way. It goes away from the surface normal, right? So when you keep on increasing your incident angle, if I keep on increasing this, this angle also keeps on going this way, right? So if I increase this angle, this angle will increase because always it goes away from the normal. So there comes an angle which is called the critical angle, where when you send a light ray with this angle, now it goes along this surface. So it still follows the same rule where it doesn't follow the same path. It bends away from the surface normal. So at this angle, what happens is your refracted ray, so this is your refracted ray, is now going along the surface between your two mediums. Okay, and this incident angle is called the critical angle. Why is it critical? This is the highest angle where refraction will take place. After this, something else will happen. Okay, because right now it is at the surface. After a while, if we increase the angle more than this, it will not go to this medium. It will not go to air anymore. It will come back to the same medium, and it is called total internal reflection. So I will go to this in a second. And I have a question here. So is Snell's law valid here? So can we apply Snell's law to this example? So to this situation. So I got one answer. Can I have more? So I got no's, yeses. Last class gave me only no's. So this class gives me both. Okay. So I got equal number of no's and yeses. 3 yeses and 3 no's. So the answer is, so I got 4 yeses and 3 no's. Yes. Is Snell's law valid? Yes. This is still refraction because this refracted ray is at the surface, right? This has gone to the next medium. It is in the next medium. It is in the surface of the two mediums. So this is like the limit where refraction can happen. So we can apply Snell's law to this. So let's apply it. So this is water, right? So N, and they have given the refractive index N1 to this, N2 to this. So let's write it. So N1 times sine theta C. Theta C is the incident angle, or in this case, it is the critical angle. It is equal to N2 times, so what is the angle here? So I'm getting answers, yes. So it is 90, right? So we always measure the angle from the normal to the ray, right? So from the normal to the ray, it is 90 degrees. What is sine 90? 1. So if you plug this in the calculator, you will see that this is equal to 1. So if I write sine theta C, I get N2 divided by N1, and theta C is given by sine inverse N2 divided by N1. So the interesting thing is, this will happen only when light goes from a denser medium to a rarer medium. If it's the other way, this will not happen, because if it's the other way, light will keep on coming towards the normal, right? So this is very important. When this thing, that means total internal reflection or having a critical angle, is only valid when light goes from a denser medium to a rarer medium. So here light went from N1 to N2, right? So your N1 is higher than N2. N1 was water, that's the first medium. It went to a rarer medium. So N1 is higher than N2. So are you okay with the critical angle? Okay. So whenever the incident angle, here theta 1 is the incident angle, is greater than the critical angle. If you send a ray which is greater than the critical angle, what will happen? It will not be refracted. It will come back to the same medium, and it is called total internal reflection. And my question, is Snell's law valid here? No. So heads are nodding in the correct way. It's not valid here, because there's no refraction happening here, right? It is completely, these two, both the rays are in the same medium. This is a reflection. This follows the reflection rules. That means this theta 1 is equal to this theta 2. So these two angles are the same. It is like a normal reflection. Okay, so you have to be very careful when you see light going from a denser medium to a rarer medium. You have to first check if your angle is less than the critical angle. If that's the case, only you can apply Snell's law. Okay, so there are two problems here. So do these two. The first one is just finding the critical angle. Second one is testing. You have to test whether it's less or higher than the critical angle. So I'm getting so many answers, and almost all your answers are correct. So first I will mark the answers. So for this one, the answer is D, and for this one, the answer is A. Let's see. First one, what is the critical angle for light traveling from glass to water? So it is going from a denser medium to a lower medium, rarer medium. So I'm bad at remembering that equation. So every time I do this, I draw a diagram. Okay. So this is my critical angle, and this is my denser medium glass. This is water. So we know at the critical angle, the refracted ray is 90 degrees. So I draw this. I quickly put the Snell's law. So in glass is 1.15. Sine critical angle is equal to in water 1.33. Sine 90 is 1. So my theta C is sine inverse. This value 1.33 divided by 1.15. Oops. Sorry, not 1.15, right? 1.52. Sorry. This cannot happen. 52. Okay. 1.52. 52. So when you plug these values, you get 61.0. You get that exactly. So answer is D. Next one. A substance has an index of refraction of 1.46. Light is passing through it at 53 degrees. At what angle will it leave into the air? So what they're saying is light is coming with an angle like this. And the important thing here is, can you see that light is going from a denser medium to air? So whenever you see that, you have to be careful. You have to check if the incident angle is less than the critical angle. If it is less than the critical angle, then you can apply Snell's law. Otherwise, you know, total internal deflection will happen, right? So step 1, find critical angle. Step 2, compare with it. If incident angle is less than critical angle, then you can apply Snell's law in the normal way. That means refraction can happen, right? If your incident angle is higher than critical angle, what will happen? Total internal reflection will happen. That means your ray will bounce back to the same medium. It will not go to air. So that is what we are going to see. So let's find the critical angle. So this is my substance. This is air. So when it comes at critical angle, it will go 90 degrees. At 90 degrees. So 1.46 times theta c, sine theta c is equal to air is n equals 1 and sine 90. Sine theta c is 1 divided by 1.46 and your theta c will be sine inverse of that. So when you plug this in the calculator, you get 43.23. So this value, this is my critical angle. The incident angle is bigger than that, right? So this is the case. So 53 is bigger than 43.23. So this is the scenario, right? What is happening? So when your incident angle is higher than the critical, it will bounce back to the same medium. It will not leave the medium. So your answer is A. Okay. So I know like y'all can direct some of you might have directly applied Snell's law and When you get a weird value for theta, then you decide this cannot happen. So that is also possible, but this is the most correct explanation. Okay, this is the most logical way to do it. So are you okay with this? Does it make sense? Yes? Okay. So there are two problems here. I want you to do these two and tell me the answer. Okay. So I will start the first one. Okay. So your answers are correct. The answer for this one is B. So they are saying light enters a substance from air at 30 degrees to the normal. It continues through the substance as at 23 to the normal. So it comes from air 30 degrees to a denser medium. And they have given this angle as 23. This is air, this is the substance. We know N of air is 1 and this one we don't know. So in this example, in the first part of the problem, we don't have to worry, right? Because the light is going from a rarer medium to a denser medium. So we know we don't have to worry about the critical angle or total internal reflection or anything, because this is a normal diffraction. So we can use Snell's law to find the index of diffraction of this medium. So for the first medium, it is air. 1 times sine 30 is equal to n times sine 23. So your NF is sine 30 divided by sine 23. And you get, what do you get? 1.2797 for this. So we know the index of refraction for the new substance, and they're asking what would be the critical angle for this substance. So now they are talking about the critical angle, and we know how to find the critical angle, right? Critical angle is when it goes from that medium, the denser medium, to a rarer medium. So when they refer to a critical angle of a substance, usually they compare it with air. Okay, so normally they compare it with air. So if you like search online the critical angle of something, what they give is in comparison to air. So that means your second medium is air. So you can directly find this, right? So this is theta c, sine theta c times 1.2797 is 1 times sine 90 is also 1. So your theta c is sine inverse 1 divided by 1.2797. So your answer will be 51.4. Okay. Okay, so the next one is the hard one, right? So let's see what's happening with that. So there is a prism and they have given us this apex angle, this angle, which is 75. So this problem I got from the textbook. That means they can test problems like this. And they're asking what is the minimum incident angle for a ray if it is to emerge from the opposite side, not be totally internally reflected. So they don't want it to be totally internal internally reflected. So it doesn't want it to come back to the prism. So there are two surfaces, right? There are two interfaces where refraction happens. This is the first interface. When it goes from air to, let's say this is glass. And the second interface is when it goes from glass, from here to air again. So what is your critical surface? What is the surface that will decide if your ray will be internally reflected or not? This surface, right? The second surface. Why? Because here your light is going from a denser medium to rarer medium. So dense to less dense. So I will call this surface 1 for now. So this is your main surface that you have to figure out first. Then once we figure out this, then we can go to this one. Okay. So let me erase a little bit. So this problem is not hard if you can figure out the angles. So angles is the hard part in this problem. So let's draw a prism and figure out what is happening. This is 75. Like I said before, this is your determining surface. So for it to be not totally reflected, for it to not happen this, your incident angle here, this angle should be less than or equal to your critical angle, right? Then this angle will go along the surface and not come back to the medium. So that is like the condition, right? So here, so if I draw something like this, no, my diagrams are bad. Okay. So you want your reflected ray to be refracted ray to go like this. That's the the limiting condition, right? For total internal reflection not to happen. And your incident ray here, this one, should come with the critical angle. Okay. Okay. So we can find out this theta c using Snell's law. We know how to do that. But the problem is that is not what they're asking. They want to know this angle, the angle right here. So let me complete this. So since this is like the denser medium, okay. So they need this angle. So how can we? So we know how to find theta c. Now we have to figure out a way to connect this theta 1 and theta c. So that's the hard part. Now let's see what we can do. This is my normal, surface normal that I drew. If this is theta 1, let's say this is theta 2. So we know the relationship between theta 1 and theta 2, right? We can use Snell's law for that. Now let's try to figure out the relationship between theta c and this. So if this is theta c, what can you tell about this angle? This angle which I marked from across. What should that angle be? If this is theta c, this is 90 degrees, right? So this should be 90 minus theta c. Are you okay with this? Yes, okay. So this is 75. They have given it in the problem. This apex angle is 75. This is 90 minus theta c. Can you tell me this angle? What should this be? So this is a triangle, right? So this is a triangle. This is 90 minus theta c. This is 75. Can you figure out this angle? It should be 180. That is angles of a triangle, right? Minus 75 minus this angle. What is it? 90 minus theta c. So when you subtract these two angles, this equal sign, from 180, you should get this angle, right? Angles of a triangle. The three should add up to 180. So 180 minus this and this will give you this angle. So when I put that in the calculator, 180 minus 75 minus 90, I get 180 minus 75 minus 90. I get 15. 90 and 90 becomes plus, minus and minus becomes plus here, plus theta c. So do you agree with me up to here? 15 plus theta c. Yes. So what can you tell about theta 2? This angle. What is the relationship between this and this? Forget about this theta 2. Theta 2 is what? It is 90 minus this angle, right? This is 90 degrees, right? This is surface normal. So 90 minus this angle right here will give you the value of theta 2. So 90 minus 15 plus theta c will give you the value of theta 2. So if I do this, I get 75 minus theta c. Okay, now we have a relationship between theta c and this. So my first problem to you is find theta c and tell me the answer. Let's go like that. So I'm also starting to do that. Find theta c. So to this surface, I'm going to apply Snell's law. N glass 1.58 times sine theta c is equal to 1 times sine 90. So from this I get theta c I think most of you all got this part right. I got answers for this angle. Theta c. I got 39.265. So we have theta c and also we know the relationship between theta 2 and theta c, right? So what is theta 2? Theta 2 is 75 minus theta c, which is 39.265, which is equal to 35.735. So now we know theta 2. Now we can figure out theta 1, right? Snell's law again to the second surface. So this is the first surface. For the second surface, if I put Snell's law, 1 times sine theta 1 is equal to 1.58 times sine theta 2. Theta 2 is 35.735. So theta 1 will be sine inverse 1.58, sorry, 35.735. That's it, right? Divided by 1. So when you do this, you get the answer 67.335. 67.335. So the answer theta 1 is 67.335. So practice this problem few times, because I saw in the lecture they have done a prism, but their prism was easier than this because they had given one of these angles. Okay, and this was an example from your textbook. Okay.